This is our presentation for the ETSET 462 final project. The project we chose was a ball and beam balancing system. This was made by Matthew Henriquez, Avery Betancourt, Reyes Moman, and Brandon Fassler. The objective is to construct a seesaw-like mechanism that can balance a ball near its center point. To achieve this, we're using an ultrasonic sensor to continuously detect the ball's position along the beam. Based on this feedback, a servo motor adjusts the beam angle in real time. The core of the control mechanism is a PID controller, which calculates the required angle adjustments to keep the ball stable and centered. As shown in the diagram, the system relies on precise feedback loops and mechanical responsiveness. This demonstrates a fundamental application of control system engineering. This slide outlines the design process we followed to build this project. We began by constructing the physical system. This involved creating the mechanical design, gathering all necessary materials like sensors and servos, and assembling the structure. Next, we programmed the system. This started with designing the transfer function to model the system's dynamics. We then implemented the PID control logic using the Arduino IDE and continuously tuned the controller parameters to achieve stable performance. Finally, we tested the system under different conditions to ensure the ball remains balanced around the center, and made adjustments where needed. This iterative approach allowed us to refine both the hardware and software components for optimal performance.
The materials we used for this project consisted of various electronic components and some craft materials. We used a 5-volt servo motor to control the angle of the beam and an ultrasonic sensor to locate the position of the ball on the beam. The system was controlled using an Arduino Mega 2560, and the electronic components were connected using breadboard jumper wires. We placed a small foam baseball on the balance beam, which was created using pieces cut from a large sheet of foam board. We used this material to keep the structure lightweight and easy to assemble. Here's the block diagram of our system, which has a PID controller and a feedback loop. The target ball position is the desired position of the ball on the beam, and it serves as the reference input for the system. The first junction computes the error using the target ball position and the measured position. The PID controller processes the error signal and generates a control signal to adjust the beam angle to move the ball towards the correct position. The PID controller uses the current error, accumulation of past errors, and the predicted future error to decide the best angle. The second junction adds external disturbance such as vibrations from the servo, friction from the movement of the ball, and electrical noise. From there, the servo affects the ball's motion by physically changing the angle of the beam in response to the PID output and any disturbance. The system output is the actual physical location of the ball. The ultrasonic sensor measures this position and sends the feedback to the first junction to close the loop.
To tune our PID controller, we used the Ziegler-Nichols method, which gave us a structured way to find starting values. We gradually increased the proportional gain until the system began to oscillate consistently. This gave us the ultimate gain in period, which we then used to calculate initial PID values. We refined those values through testing and landed on a KP of 2.5, a KI of 0.006, and a KD value of 2.6. Each of these terms plays a specific role. KP reduces the overall error by reacting proportionally, KI eliminates steady-state error by integrating over time, and KD dampens the response to prevent overshooting by reacting to the rate of change. This graph here illustrates our system's behavior using these final PID values. The orange line represents the reference position, the blue line shows the actual output, and the yellow line is the error in between them. Ideally, when the output matches the reference, the error should be 0. However, in this graph, the error signal has been intentionally offset vertically for better visibility. This offset allows us to clearly observe the trends in error alongside the other signals, even though it's not shown exactly at 0 when the system is on target. As you can see, the output tracks the reference smoothly and stabilizes quickly, demonstrating strong control performance with minimal overshoot and good steady-state accuracy. We also derived a closed-loop transfer function using these PID values, which confirmed the system's stability and expected behavior. For testing, our main goal was to ensure each component of the system performs accurately and contributes to stable ball balancing. We broke the system down into 4 main parts. We first verified the ultrasonic sensor by checking its accuracy at various distances, ensuring consistent and reliable readings while filtering out noisy data. Next, we tested the servo motor for speed, range, and how quickly it responded to control signals. Then, we evaluated ball movement, observing how different weights and surface interactions affected its behavior on the beam. Finally, we tested the entire system, comparing open-loop and closed-loop performance. Through careful PID tuning, we successfully stabilized the ball around our desired reference point. which is about 10 centimeters from the sensor located between the beam's midpoint and the servo connection. So in this video, we're showing the system running with optimized PID values. You can see the beam actively adjusting as the ball moves towards the desired reference point, which was about 10 centimeters from that sensor, like I previously said. Once the ball reaches that position, the system stabilizes and holds it in place with minimal movement. In our full demo video on YouTube, we also showcase the system's behavior in different states, including an open loop mode with no feedback, a poorly tuned PID with instability and overshoot, and this final version with properly tuned gains for smooth and stable performance.
To end with, we had the lessons learned throughout this project. First was that tuning a PID controller is more hands-on than expected. We could get the system to balance, but it took a lot more trial and error than we thought. We thought we could just plug in the values and work, but because of the ball not perfectly fitting the balance beam, because of the low weight of said ball, and the low friction, it changed things up, so we need to adjust our values more so they can properly balance the ball and adjust in time and not chaotically. As well, we learned that sensor placement and noise filtering are critical for good correction and good balancing. Small changes in the setup or inconsistent readings just had a massive performance or massive impact on the performance of the balance beam. Occasionally, our original sensor was reading 50, the max value, for no reason. Even our new sensor occasionally read, I think if I remember correctly, 1000 once or twice, and we need to figure that out. It was a lot, but once placed correctly and filtered out of the noise, it worked very well. So you need to make sure you filter the noise correctly. As well, it's very, very, very advantageous to work in modular coding. If you make everything in modular coding, that means you can much easier go back through every section and debug. If something is wrong, you can go section by section to find where the problem is, and then you can proceed to find the problem in the section that you can find which section it's in and find the problem within that section. Makes it a whole lot easier. Finally, the clear role division throughout our team helped things tremendously. Once we made sure everyone was sectioned and could help each other, but knew what they were doing, it helped things flow much, much smoother, and everyone worked well on their individual parts. For the actual technical distribution in total, here was how everything was about split up. I think it worked out really well with the project coordination and system modeling. Avery did about 30%, I did about 40%, Matthew did about 20%, and Rice did about 10%. The PID controlling design and tuning, Avery did about 25%, I did about 20%, Matthew did about 25%, and Rice did about 30%. For the hardware assembly and the motor and sensor integration, I did 10%, Avery did 10%, Matthew did 30%, but Rice took the bullet on this one and he did most of the hardware assembly. With a very nice blue board. And finally, for the microcontroller program and real-time testing, Avery did about 35%, I did about 30%, Matthew did about 25%, and Rice did about 10%. Overall, it worked out very well, and I'm glad the team worked together like this. That is all. Thank you very much for listening to this presentation, and have an excellent summer.